Hello everyone, whoever is present in the class, please be attentive and ask questions as much as possible. So we are now dwelling on a different subject, which I named as Art of Programming, if you know. So here we won't learn just programming, we'll learn how to code in a better way. So the first thing is I'll write what is my intention. What's my intention regarding teaching this? Because there are a lot of Python tutorials online and there are a lot of books available. So why am I do it again from the scratch? So the first thing is what I want is I want you guys to learn computational thinking. So I would like to inculcate computational thinking. So what is this? What is this computational thinking? So this basically is a problem solving process. So in which what we do, if we have a real world problem, we break that down. So once we break that down and into smaller problems, manageable parts, and then we think computationally. If it's a real world problem, how to get into mathematical world and how to do computation on the problem. And every problem can be thought as a mathematical problem that we have seen in the functions. So we took a different real world problem and there what we did is we tried to map into the mathematical world. So here now once it's in the mathematical world, so we can apply computations on that. So usually what we will do is you will decompose the problem. Let's suppose you have a real world problem, you will decompose it. That is the first step that you'll do. It will be a huge problem and you will decompose it. Basically you'll break it down and that complex problem will be broken down into smaller parts and more manageable sub problems rather. So let's suppose when you are designing a video game, you can just break it down into different components like game logic, what is the graphic that we'll use, what is user interface, how will we handle sound and stuff like that. Okay, and then once you break it down and you will have to get the computation within. Okay, you don't have to just see the problem, and all the real world problems usually are solved in this way. So when you see a real world problem, even when you see construction of building, so there also you decompose the problem, you make the problem smaller so that it is manageable, and then you do a physical work on that. Similarly, whenever you see a real world problem that can be solved by computers, so what we do is we'll decompose the problem first, and then after that we'll recognize some patterns into that. Pattern recognition. So why is it important? So that you will write an efficient code. So if you can see there's a trend in a problem, there is some overlap in the problem. Sometimes some problems may look very big, but once you decompose them and you can see that some parts of the problem they get repeated, and you have to see that patterns. Okay, and this comes under why I'm saying that this comes under computational thinking, because you will have to think computation. Now you have to put yourself in the shoes of a computer, in the shoes of a machine. How will machine perceive this problem? So now you no longer will be basically a human thinking for himself or herself, but rather you will be a human thinking for a machine. How should I make machines understand? That's why you have to decompose the problem. You have to recognize the patterns, and then you will abstract. Okay, you'll abstract all the things. Abstraction. So what is this abstraction? As you have seen that in functions, we said this if one quantity is dependent or has some relation on some other quantity. So we have a template of the problem solving now. If any problem follows into that category, we now don't deal with the actual problems. We'll abstract to the details. The only thing we care about is that one quantity is somehow dependent or is somehow having a relationship with other quantity, and we can solve it with the functions. Similarly, once we decompose the problem, once we saw some patterns, then we'll abstract other problems. You will go far away from the real world problem. You won't care now I'll only solve that problem. You'll basically create a layer of abstraction, and after that you will design the algorithm. I'll say algorithm design. These are the usual steps that you involve, and maybe these steps you won't even feel that we are doing, but in real world that's what you do. You take a problem and you understand it, you decompose the problem. If it's a big problem, you'll decompose the problem. Once you decompose it, then you try to find some structure in the problem, because the thing is that the problem may be humongously large, and then you will have to have a manageable portion. So once you decompose that, and after that you see some patterns in there, you see some overlaps in the problems. Okay, once you see that overlap in the problem, and after that what you do is you do the abstraction. You now go away from the real world problem, you bring in these notations, you bring in these variables, symbols and stuff like that to have a level of abstraction. How I explain abstraction usually, let's suppose you are driving a car. Now that you know a mechanism is there, there is an interface in the car. You have an handle in the car, you have brake, clutch and gear, brake, clutch, gear, and then you have accelerator. This is your interface, this is what you deal with. Inside you don't care that if it is an engine that's running the car, if there are some people who are just walking. You have an interface, you don't care what's underlying mechanism. Similarly in the phones, there may be some other hardware, but you are given an interface. The details are being abstracted out. Whatever the dirty details there are, whatever the jargon there is underneath the hardware, whatever hardware you include, you don't care about that. The only thing that you care about, what is my interface? That's what abstraction is. So in mathematics usually, or in computer programming, more or less what you will do, you'll understand the problem, then you will abstract it out. And you will bring in these symbols and you will bring in these functions and stuff like that to abstract the problem. And then you will design the algorithms accordingly. That's the first thing I want you guys to learn. If you see a problem, you should have this computational thinking. It takes age to learn. Okay, you should have this computational thinking. You should think computationally always. Okay, how to do this, how to do it computationally, how to do this computationally. And once you see a problem, if you have this thinking inculcated such that this is subconscious for you, when you see a problem, subconsciously your mind should trigger, okay, how can I decompose the problem? Okay, how can I recognize pattern in that? How can I abstract the details? And then how to design algorithms. That is what basically the programming should be all about. It's a quote by Steve Jobs. Somebody he said that I want everybody in the world to learn programming because it teaches people how to think. Okay, so what programming basically does is it teaches people how to think. That's really important. This thinking process is really important. Okay, because now you are not being a human. In human, when once you communicate with me, right now I'm communicating with you. In this, I assume a lot of things. I assume that you know English. I assume that whatever vocabulary I know, you also know that. And similarly, you know, we in the normal communication, we assume a lot of details, and then we communicate. But in the computer science, when you're talking to a machine, you have to address all of these assumptions. Okay, you cannot say, okay, probably computer knows this, probably computer knows that. Computer is just a dumb machine, just maybe nuts and bolts, maybe some wire is there, and you'll have to make it understand. You'll have to make a world first. Okay, for the computer, you'll have to make a computation world, and then make the computer think. But rather, in our real life, how do we communicate? We are living in a world. The world is set up for us. There is a language set up for us. We have all these assumptions are there. Then we talk. Then we communicate. But once the computer is built, okay, there is some environment set up. Okay, I'm not speaking about the computer literal environment. There is a meaning associated with the environment in programming language. I'm saying that once you build these wires and these adders, multiplier, these circuitry boards are there, you basically have an environment to talk in. And once you have that, after that you have no assumptions. You have to teach computer everything line by line. Okay, it's basically a dumb machine. The first goal is that I'll try to inculcate in this computational thinking. Once we take a problem, we'll try to decompose, see the problem, see the pattern, and then abstract it out, and then I'll design the algorithm. Then probably we'll learn some Python. So how to now solve the problems. Now we have to talk to a computer. Even if you know how to solve a problem computationally, you break it down, you broke down the problem, and you designed an algorithm. Still, there should be some medium of communication between you and the machine. So that thing, the medium of speaking that will speak with the computer is Python. Okay. So because why is it, why are you choosing Python? Because it's easy to learn, really easy to learn. I would have loved that you started with C, C++, probably assembly, because that gives a lot of hardware details, but you will probably feel overwhelmed by that, the details that these languages have. So it's better to start with Python so that you have some sense about what programming is, how to achieve different tasks. Okay, so that's why I chose the language Python. And one more reason is that in machine learning AI, this is the most popular language, because most of these projects or most of the libraries, they are written in this Python. Okay, their base code is basically in the Python. So that's why I chose the language Python. And probably we can also look at some language like R, which has better package regarding the statistics and stuff like that. And after this, once you know that how to think computationally, what is computational thinking, once you got that, and now you also know a language. Okay, you know how to talk to a computer. Now you should learn how to better talk to a computer. So I'll probably teach you how to write better code. So what's the meaning of better code here? So code that is readable. So let's suppose you guys will be working in the teams. In your future career, you will be working in the teams. You can't be alone, Einstein. If you know everything, every detail in the world, and you just have to work alone on that, probably you won't achieve much. So it's better to work with a team, so that team, it gives different ideas, and many people will be working on different things, because usually it's a modular design. So you have to work within the team. So your code should be readable. Okay, because usually what they say is code is written once and read multiple times. So it is better to better to write a code which is readable. Okay, this code should be human readable, because it's read by humans also. So sometimes I have seen people written beautiful code, But the problem with that is you need a very high level of expertise to understand that code. Machines don't understand that code because if the guy is programming since, let's suppose, 10, 15 years, and he writes very beautiful code. But once he works with the team can understand the code. Okay, then it becomes a bottleneck. Other people take hours and days to understand that code. So it's better once you start your career, you should have a habit of writing a code. So there is a taste in the code. So you can do one thing, other person will do the same thing by using different syntax, by using different techniques. So you can see there's a taste in the code. So everybody has a different taste in the code. Once you become good programmers, once you achieve that level, and you will feel that taste, and you will see this beauty in the code. Okay, now you won't see that just as numbers and just these colored things there. So you'll see there is a beauty in the code. Sometimes you'll have aha moments. Sometimes you'll see, oh my god, I have never thought that this code can be written in this way. And this is so succinct, so beautiful. Okay, everybody will have a taste of code. Everybody has some beauty aside the code. I don't want you guys to write the code which people will feel ugly. Oh, this is so ugly. So write in beauty, not in terms of aesthetics. Okay, you will write just colored codes and this stuff like that. Beauty in terms of how you write, your style. There's a coding style. Okay, I can easily recognize if somebody submits an assignment. I can easily tell you what's the experience of the coder, how much has he coded so far in the life. If somebody is a beginner, probably they will write the code. It's whole mess. Then if somebody is a little bit intermediate, you will see the code is a little bit beautiful. But if you see some advanced coders, there is a beauty in code because they have really good coding style. Okay, so I want you guys to learn the better coding style, and you will have to have modular design. You should handle the errors. Okay, you should know good naming conventions, and you should put in habit of commenting out the code. This is really important. Once you go to the industry and you write industry grade code, and there these things become really important. Okay, and nothing can stop you from writing that. If you sort of focus on only learning Python, that's not my job, because there are humongous number of tutorials available online. But the thing that I want you to get from these sessions, from these lectures, is first is computational thinking. Probably second, you can learn Python. That's not a big job. The big job is that how you can write better code. And after that, being computer scientist, you won't be a mechanic. No offense to mechanics though. There is a difference between a mechanic and an engineer. A mechanic can fix a car. He just hears the sound and sees the condition of the engine, and he can see the problem is here or something like that. But an engineer, an automobile engineer, understands why is this problem arising. So that's how you should see these computers now. So once you code, you won't just code. So your code should be efficient. Okay, once you write the code, okay, the first thing is you will be really good at computer thinking. You compute once you saw the real world problem, you broke it down, saw the pattern, abstracted it out, made an algorithm, and probably you'll code it in Python. Then once you code in Python, now I said you will have a good coding style. Once you have that coding style, then you will have to think, how can I efficiently write this code? There are ways to minimize in terms of computers. Efficiency can be seen as in terms of space and in terms of time. My written algorithm should take least amount of space possible, and my algorithm should take least amount of time possible to run the code. Okay, there you will see what time complexity is, what this space complexity is, and what are these asymptotic notations. We'll also do some algorithm analysis and stuff like that to get the optimality. These are the 4 things that I want you guys to take out of these sessions. Probably we'll have a couple of sessions to this art of programming. So there you should learn this. So there you should first inculcate. I'll just summarize these points. The first thing is you should get computational thinking. Once you have that, and you learn a language. I'll say you learn Python. But you will not just learn, you'll learn the syntax of Python, and you will learn probably the whole programming itself. If you are then given a task that write a code in C or C++, probably you'll be better off by that. You just have to learn syntax after that. Okay, and then the third point I said you learn is how to write better code. So you learn to write better code. Better, I told you what better in terms of style, in terms of taste, beauty, coding style. Okay, and the fourth thing that I said is you will write efficient code. If you got these things out of these couple of sessions of the Python or art of programming, I'll consider that you guys have learned something. Otherwise, I'll say that everything has been wasted. These sessions have been wasted. Any questions? Let's now start this art of programming. The first thing I wanted to tell you, I will get a little bit philosophical. So I'll see what are the types of knowledge. Okay. So mainly we can categorize knowledge into two things. The first thing is called as declarative knowledge. Okay, what is the declarative knowledge? So this refers to a knowledge that can be stated as a factual information. Let's suppose I'll say the capital of France is Paris, or I can say, let's suppose water boils at 100 degrees centigrade, or in Bangalore today's temperature was 36 degrees centigrade, or something like that. All these are somewhat factual. Okay, you can verify them. They are declarative. I'll declare something. Okay, and this probably definitions you can write on your own. I won't write the definitions. Once you see these videos again, you can make notes and write them. Otherwise, it will take a lot of time for me. The second knowledge is called as imperative knowledge. Declarative means you are declaring a fact. As I said an example, the capital of France is Paris. I'm just giving you a fact. It's a factual information. The second thing is imperative knowledge. So imperative knowledge basically is how to. It's a recipe. Okay. So this type of knowledge involves instructions or steps for doing something, or how to do something. It's like a recipe of cooking. Okay. It has certain, or maybe let's suppose if you are given a furniture, how to assemble that furniture. You will be given steps. So here, so I'll write this is basically factual, and you will declare something, and this is somewhat how to, or a recipe. Okay, something like that. And now programming basically comes under this imperative. You will have to give stepwise procedures. So programming is all about writing these recipes. So why do we write these recipes? Because to generate these facts. Okay, we'll write something and you will generate the facts. Now you see how do we merge these two things? How do we merge declarative and imperative knowledge? So now you have a stepwise procedure which will land at some fact. Okay, let's suppose I wrote a program. I wrote a stepwise procedure. Okay, I'll just give it a number. I'll give it a number 4, and this program, let's suppose, calculates square of the number. So this is x square function. So this will give me 16. So I can say square of 4 is 16. This is the declarative knowledge. So how I achieved this is by using the imperative knowledge. I said you the how to procedure, how to basically achieve this. This is what programming does. So programming, so I can write this, it somehow fuses these two things. So what programming does is, programming is writing these recipes to generate the facts. So in programming we write algorithms or we write code. Usually I'll call this code recipes that generate or manipulate these data to produce these facts. Okay, a program can let's suppose calculate area of a circle. You will just give the radius, it will calculate the area. So underneath there will be a stepwise procedure that will basically give it imperative definition or imperative recipe how to generate this area. Is it clear? So if I say, let's suppose y multiplied by y is equal to x. So this over here, if you see this, so this over here is directly factual knowledge. So I'm just giving some facts. Okay, once I have to tell you how to implement this. If I tell you how to implement this, so that is what an algorithm consists of. Okay, if I now have to compute the square root. Okay, if I say y square is equal to x. So if I have to find a number such that if I have to find this y. Let's suppose we have to find this y. I am being given x. So x will be given to me. X is given. So I have to compute y. Y is to be computed. So basically this is the relation. So the question basically that asks me is, what is the square root of x? Okay, that square root of x is y, and it should hold this relation. So I'm just declaring something. So then I have to compute a stepwise procedure. So how to compute that? So there will be a sequence of steps. So let's suppose I'll write that sequence of steps. So I'll say the first step should be start with a guess. Start with a guess. Start with a guess. Let's call it g. Okay. Then the second thing is multiply g multiplied by g, and then square the g and see if it is close enough to x, and see if it is close enough to x. If it is close, then you can stop. Okay. If it is not close, otherwise what should you do? You should make a new guess. This is the second step. This is third. Otherwise, make a new guess. Now the guess should be smarter. Okay, we should somehow approach towards the solution. We should not just randomly guess. Otherwise, it will be like a drunk person walking on the road, and he has to go somewhere. He doesn't know where to go. But here the problem is I have to find the square root. I said first make a random guess. It's all right to make a random guess at the first position. The second thing is see if this guess is somewhat accurate. Now you should find a clever algorithm. You should somehow find a clever way in which I'll approach towards my solution. So what's the clever thing? So I said if this guess is not close enough, so what should you do? Make a new guess such that you can do this. You can say g plus x divided by g divided by 2. You take an average of these things, and this is your new guess now. So this is your g dash new guess. So you take the original guess, whatever you guessed initially, and then what you do is you take this number x and divide it by the g. Once you divide it by g, and then you average it out, and this will guarantee you mathematically, this guarantees you that you'll get closer towards the square root. And I can prove this mathematically already. So this is now your new guess. The fourth step is use this g dash, basically use the new guess and repeat the process, and repeat 2 and 3. Okay, you should repeat these two things till you stop this. Okay, now if you see this algorithm, so what we have there, so here the first thing we had sequence of simple steps. If you see, we had some 4 steps. They're not complicated, they're simple. Probably sometimes you might, this is a subject term, complicated is a subject term. So here if you see that these are some steps. If I can just say, for me it might be simple, but this is some sequence of steps. That's the first thing. The second thing is there is a flow of control. Okay, this is the first thing. And the second thing is there is a flow of control. So what I mean by flow of control is that first I'll execute this, then I'll execute this, and then I'll execute this, then I'll execute this, and once I execute this, I'll repeat this again thing. So there you see a flow of control is there. So you have to control the flow. Usually each step is executed once at a time. So once you can just control this flow, because your flow is constantly going downwards. Sometimes you can go upwards also. Okay, and in programming language there are different ways by which you can go backwards. Okay, in the initial days people used the go to statement, then we came up with while loops, for loops and stuff like that. But you can see that clearly that there is some control flow. Flow means how the code is going. Control flow means how to control that flow now. So if I have to just have 1, 2 and 3 and 4 step, but now I want to go back, I wanted to go back here, so I need to control this flow. The first thing that you saw in an algorithm, so this over here is an algorithm. So in this algorithm you saw there is a sequence of steps involved. And the second thing that you saw is there is a flow of control. Okay, there's a flow of control process which specifies how each step and when it should be executed. Okay, and the last step is there's a way to stop. Way to stop. So you saw that here we had this way of stopping. Somehow some condition is met and then we have to stop. And there are some algorithms, this is a big problem in computer science. We have some problems called as non-halting problems. So you never know that if the algorithm is right or not, because your algorithm won't stop. So usually we want algorithms that they should stop after some like determined step or after getting an answer. Okay, which stop. That's why I have said if g multiplied by g is close enough to the x, then stop. This is my stopping condition. Otherwise your algorithm will run for infinite time and you never will know if this algorithm is computing or if it got crashed or something like that. Okay, now you have interfaces. Like lucky that you have interfaces, but initially when there were computers which were no interface, had no interfaces, they basically were just mechanical machines. They were moving, they had moving parts. So you have to figure out if it's doing something. So parts were moving continuously, but that's what the problem, non-halting problem came in. The machine was not stopping, and probably we had dilemma right there. So what dilemma was there? So we had a dilemma. Machine is computing something. Machine is computing. This was the first thing that was in the mind. And second thing was probably it is never reaching the solution. It is in the infinite loop. Okay, sometimes if the machines think like if a machine is physical, you have no physical, you have no that virtual this interface like a screen. You see these mechanical parts moving. You are waiting for the computation. You are thinking that machine is always this is computing. It will stop, and 2 days pass, 3 days pass, 4 days pass, and it's still computing. Then you probably might say this went in infinite loop, and you are not sure, and you may stop the machine, and probably your machine was close to the answer, but you never knew it. So this is called as non-halting problem. It's a very famous problem is in computational theory. There is something called as theory of computation. So there is a very famous problem, non-halting problem. So what I'm saying in our algorithm, it should have some halt. It should have some stopping point where it should stop. So now you saw an algorithm. You saw this algorithm. Algorithm is nothing but a recipe. So what basically is an algorithm? I would have talked about history of algorithm, but it will take too much time for where algorithms came from. So I'll just say one thing I'm proud of, that this algorithm term was given by Musa al-Kharzmi. And I'm fortunate that he shares the name with me. And this algorithm now, what it does is, it somehow is a recipe, and once you give it something, it makes this knowledge as declarative knowledge. You'll compute some facts out of it. You'll give a recipe. That recipe is basically imperative knowledge. Once you give an input to it, and it will produce an output. In a way, it's a function. If you see, in a way, it's a function. All the programs are basically nothing but giant functions. Maybe they be multiple functions. Now all of these functions are put together. Probably we'll add them, we'll compose them together, and somehow we'll do that, and we're performing computation. So everything you do is probably mathematical. Okay, underneath it's all mathematical there. So once when you even multiply things, probably you are printing something on the screen. Everything underneath going is is something mathematical, and you saw that all of these can be put in the functions. That's why these subroutines, they get the name from of these functions, because we call these subroutines functions that we'll see in the subsequent classes. I hope that you saw the algorithm. So what algorithm has now, we saw there are some sequence of steps involved, and usually it will go line by line, or probably it will go instruction by instruction, and then we have a flow of control. So what is that? Usually the flow is like going straight, and we want to control that flow. So there is a process to control that flow. In the last step, that's it. So there should be a means of determining where should we stop. So there should be that means. Is it clear? And the big question is, I have an algorithm, I know an algorithm, I have a problem, abstracted it out, now I know the algorithm. Okay, now I have a recipe with me. So the big question is how these computers and these machines execute algorithms. That's the big question. Okay, how computers, or how machines rather, how machines execute these algorithms. That's a big question. Now I know a recipe. I have everything with me. I know if this step is followed, and that I would love to know that how the machines execute these algorithms. The first thing is we have to see there are two things computers do. They perform these simple operations and they remember the results. Two things they do. So they perform calculations. Yeah, everything is a calculation. Do not think that once you walk you don't calculate. You calculate every time. Okay. And the third thing is remembrance. Remember the results. These are the two important operations. So you have to perform operations, and the operations will be basically very simple. There will be addition, subtraction, division, and these are all operations that we do. Whole of your computer science is basically dependent on this operation: plus, minus, and even I'll say multiplication. Even if you just know addition and subtraction, you're done. You know everything about maths. That's only then putting these things together. And probably I'll prove that to you, that if you know how to add and how to subtract, you can already get to multiplication, you can already get to division, you can perform modular arithmetic, and once you put these things together, you get a lot of huge things. But everything underneath is some performing some simple operations or performing some simple calculations. Okay, and you have division, you have this modulus operator, and everything. That's just these multiplication, division, modulo operator. All of these things are just some tinkering about this addition and subtraction. The only real operation that exists are these two operations, I'll say, in mathematical operations. And other things that you can basically, all these operations can be derived from these operations. Simply, if you have to, let's suppose 6 multiplied by 3. So how you can achieve it? Add 6 3 times. That's it. Basically, this is an addition operation. Division basically is repeated subtraction operation. Okay, that's how you get all of these operations. So I said the computers have two things. These machines, how do they execute programs? They have two important things. The one thing is that they perform these simple operations. I'm again using the word simple. It may not be simple for many people, but it is simple actually. Okay, why? Because human brains are so complex. So if you have a reference point at that, so in front of that, this is basically simple. So they perform these simple operations, and the second thing is they remember the results. They have the storage where they have these results. And these are the only two types of things mostly computers do, and they do the miraculous things or the magic that you see in front of you. Okay, so what kind of calculations now we do? So we will do some, what our built-in calculations are. We'll do addition, subtraction, division. Okay, you'll manipulate strings in different ways and stuff like that. Okay, so now there are two types of computers that we had. Okay, that we have seen in the history. The first thing was, this is called as fixed computer, I'll say, fixed program computer, I can call it. Probably you might not find these names anywhere, but the gist will be same. If you read the history, I have a habit of giving names to things. So, but I am just conveying the gist. Probably you might not find these names, it's all right. But you should have the idea what I'm talking about. The first thing is fixed program computers. So what's this fixed program computer? So there's a set of algorithm, so that is hard coded into that. Let's suppose you have a calculator. Okay, on a key, one number is hard coded onto that, or probably it does one function. So something is hard coded into that, and you cannot change it. Okay, that's what fixed computers are. I just gave a vague example, calculator. A calculator nowadays are like way complex than this. But if you hard code an algorithm, okay, if you want to do a one task and you just made a device which can only perform that, task. Okay, maybe I can say specific task computers. they'll only perform one task. Let's suppose you want to perform calculation, you want to add, subtract, division, you want to perform arithmetic operations. That's a task. You want to perform calculation. This calculation, they can only do one thing. Okay, they don't support any other thing. You cannot just change the program within. So that's one time it's hard coded. It's hard coded. That's why you get the calculator people put in the pockets. That's what it does. Okay, now even if you see, let's suppose earlier radios, they'll only have capture the radio frequency. Again, that's a machine doing some computation, but it's a specific task machine. It does only one thing. Okay, now people are again going back to this era. I'll tell you that history also. Now there's a lot of research going on this specific task machines, and the big idea was we wanted to get a machine which can do generic tasks. Okay, then that's where the one Neumann architecture came in. I don't want to talk about that. That will be a little bit out of the scope of this course. Otherwise, we'll have to talk about computer architecture and stuff like that. But the first thing was we wanted to build a specific task computers. If you want a specific thing, we just had this fixed program, and it can only do one thing. It had hard coded things, and until probably 1940s we did this sort of thing. Okay, where we had these things. Okay, so the program was stored in the computer. Machines had the stored. So what was there? So this was the program was there in the machine. Okay, we cannot change the program, and machine stores this and executes the instructions. Okay, so programs, they are no different from other kinds of data basically. So if you see a program, what is program? It's nothing but some data is there. Okay, I gave an example of calculator, let's suppose. So calculator is somewhat a specific task computer. So it does only one task, that is performing arithmetic calculations. Then came the thing, once people thought that can we make generic computers? Okay, that's called, these computers are called as stored program calculators, or stored program computers. They are called as stored program computers. So now what they have is they divided whole of these things. So they had an arithmetic logic unit. Okay, they have some simple where we can move data from one. So probably we have some memory like this. So we had a memory like this. Okay, then we had arithmetic logic unit, and then we had a control unit, something like this. This is how the computer was divided. Now even the data and the program was stored in the memory. Okay, this data, this plus instructions, they were stored in the memory. Okay, so these instructions, by the help of control unit, they were taken and then given to the ALU, and then ALU basically manipulate this data. You can see that coherence. I am simplifying this detail so that I don't have to explain much. So but you can see this architecture. We had separate memory, and we had a unit which is called the arithmetic logic unit. So in that arithmetic logic unit performs the operations, and then we had a control unit. Control unit picks up these instructions and feeds it to the arithmetic logic unit. You can take a simple example also. If you want, let's suppose, add two numbers, you'll say 2 plus 3. So what will happen? There will be this memory. Okay, this 2 will be stored somewhere, and this 3 will be also stored somewhere, and each memory location has a name. They have an address, that's called memory address. Now we have this part of the computer. Here we have control unit, here we have arithmetic logic unit. This is a whole subject that is studied in computer architecture and organization. Okay, computer architecture and organization. The whole they deal about this. Probably people from EC department, they would know a lot more about this. They have the microprocessor study 8085 and things like that. How that they have these address buses, memory bus, and all that stuff. I'm just abstracting of the details. Okay, I'm just giving you the gist how these things work. So now what we'll do is control unit will read. There will be instructions. Instruction is basically add 2 plus 3. The first thing it will be read 2. So first thing is 2 will be read. Okay, and it will be stored in a register. So register will have this ALU, or the processor will have access to the register. Okay, once 2 is loaded, okay, then we'll have something called load 2. Then we'll have load 3. We'll first load these 2 and 3. Once they are loaded in the registers, so ALU has its own registers. So once they are loaded, after that what will happen is ALU will get involved and it will add these two things. So it will add and give result 5. Okay, once it generates the result 5, it will have to store it somewhere. Okay, so it will say store it into this. Then control unit will go, and there it will be storing it into some memory 5. Okay, so it has a memory location. I just gave you probably like 2-minute summary of whole of this COA. So this computer organization, this is what usually are. These are called as stored program computers. Now if you have some other data, so you can you can now change data, you can change program and perform the same thing, because ALU is somewhat doing now generic calculations, and control unit is helping it to take the instructions. Okay, this is called as stored program computers. Okay, so there are the special programs written once you write the instructions. Now we have initially we were having this binary language where we just which sort of manipulated signals directly. Then we saw it's too hard. If you might have heard that there are punching cards. Okay, there were punching cards, and people used to write programs on that. They had punching cards or something like, they had holes glued into that, and these holes had meanings. Okay, wherever there was a hole, it meant one. Wherever there was no hole, it meant zero. Okay, so they just gave a punching card and punched it into the computer, and that it read basically a binary program from it. Okay, and you had to submit a job, and these machines were so slow. Basically, these punching cards were nothing but instructions given in binary. You close this wire, turn this off, turn this on and off. But then people found that this is a little bit tedious. How now we have to make a punching cards? Can we abstract the details? Humans have this nature of abstracting details out. They said, okay, can we build something on top of this? Okay, we have, machines, they understand binary only. Okay, they understand ones and zeros. By ones and zero, I mean they just understand current. In terms of current, they understand on and off. Current is either there or current is not there. So they understand only this. Now in order to make programs, we discovered punching cards. We said, okay, we'll punch the hole. Hole means one. Where there is no hole, that means zero. So why is this even called one? So here a pin can enter. So if the pin enters, it will close the circuit. So it will let the current pass. That's why it's called one. Okay, where the pin cannot enter from there, so the current won't flow, then it's a zero. Initially, we were manipulating machines at this level, but now humans said it's way difficult to do this, punching cards and then write whole the things. If there is a small problem with that, and we won't be able to, they abstract of the detail. So they brought some translators within, okay, and they came up with assembly language. So they had something called assembler. So it again was a little bit hard. If you see, it worked on register level. You will see that add something like this, add R1, R2. This basically means whatever the contents are R1, R, and then took this R2 and add them together. And then you will write instructions like this, assembly, in assembly language. So people again thought, let's abstract more details. Now from the machine code, this is called as machine code usually. Binary code is called as machine code. Machines understand this code. Okay. Then we had the assembly language. I'm just abstracting out a whole history here. There are a lot of steps involved within. So, but I'll just give the top steps, that like a high level overview of the steps. We had this machine code, and we came to assembly. We said, okay, assembly in which I'll have some English like words, but here again I'll have manipulation at the register level. After that, we came up with what's called as high level language. So these two things were called as low level language. Low level. Why? Because these assembly and the machine code, they were really fast because they were in touch with this hardware. You don't have to do much of the things. You don't have to do translation. So for machine code, there's no translation required. It'll directly run on this. But for assembly, there was only one step involved. But still, it was too hard and for the humans, and it was too easy for the machines to understand. That's why it's called as low-level code. Okay. Then we came up with these compilers, interpreters, transpilers, and there's a lot of stuff involved here. So it's a huge. So here, there's a huge research going on how to now make a language which is called as high-level language. HLL. So high level language means which humans will understand better, but computers will have a hard time. But what we'll do is, now we know that computers are very fast. They are fast on this calculation. So what we can do is we can incorporate some translators within. So if we have a high level language which humans can understand, a high level language like C or C++, or let's suppose Java or Python, all of these are high level languages. Why am I telling you all of the detail? The whole point is you should not see this language. We're just diving into the middle. Okay, and I'm just coding. You should know what is going underneath. What were the things that people were thinking once they were discovering these things, and once they were inventing these things rather. Okay, so you saw the problem. The problem there was we had machine code really hard to make, and we otherwise we would have been in the punching code era. Then we said, okay, let's bring assembly. We'll have some assembler within, which will convert this assembly into the machine code, and this is what we'll call as low level language. And still, people couldn't handle this much because it was really hard to code in that. I think in my whole life I have just coded in assembly for once or twice, not more than that. Okay, because I was born in different era. Probably if I was born 10 years before or 12 years before, I probably would have coded more in assembly. Okay, and then we had these high level languages. The whole point of these high level languages was to have the more abstraction. Now these languages should be closer to humans. High level languages are basically closer to humans. Humans do understand them better. That is the language or the syntax is like human language, like English probably. So you can see that there will be something like this if, or there will be something like else. So there will be print. All these things, if you see, are derived from English. People do understand this. Okay. So now what is going underneath is, so we have a high level language. So there is a whole steps of translation involved. If it's a compiler based language, so there's a compiler involved, and compiler has a lot of steps. So if you know, compiler has, the first thing is they do something called a syntax analysis, then they do something called a lexical analysis, and then they have a code optimization, code generation. There's a, I think 5 6 steps are involved, and each step is a research field. Okay, in the compiler itself there is a whole, in computer science probably who are undergrads here, you will learn compiler design. There's a whole subject in itself, how the compilers are designed. Okay, so there are steps involved, so how these high level languages are converted into this machine code. Okay, basically you need to see two things. The first thing is there will be a compiler involved, or there is an interpreter. Both of them has some advantage, disadvantage, but if you see, many other times you will see that people saying Python is an interpreter language. I have seen it written in many books, but Python is based on both these. Python is basically an interpiler language. It also uses compiler. It will come to probably who knows computer science, they might have just heard that it's an interpreter based language, but Python also uses compiler. So probably I'll show you once I get to coding. Right now we are just going in the details. Once I go to coding, I'll prove you that Python also uses compiler. So probably 90% of your books are wrong. So what they write is, they'll write Python is an interpreter based language. It is, but it also uses compiler. So I'll show you that this thing is due. So I'll show you that how does it use compiler, and I'll prove the point wrong. So why is it not only using the interpreter? Okay, basically the thing is, interpreter checks the code line by line. Compiler, what it does is it checks the whole code once. Okay, we'll see that. We'll see the details of these things. So we went from this low level language to high level language. So what is a high level language now? It's closer to humans. So humans do understand it better. That's where the Python comes from. And what Alan Turing proved. So there was a scientist, Alan Turing. Because the whole computation was mechanical. The computation was not like digital. The things that we saw right now, it is digital now. Before that, the computation was mechanical. People were building mechanical machines which had moving parts in that. They had all these gears and stuff was there, and they were moving. So what Alan Turing proved is that Alan Turing said that if you have only 6 operations, if you can perform 6 operations, you can perform any possible computation. Whatever is computable. There's a question: what is computable? Okay, it's a whole, there is a field basically called as complexity theory. So in that people see what is computable, what is not computable. Okay, it's a whole subject in itself. I don't want to delve into that also. What is computable, what is not, what is decidable, undecidable, these NP hard. So it's a whole subject in itself. But what Alan Turing said is, Alan Turing said that if you have these 6 operations, which he called as primitive operations, he said anything that is computable can be done. What is that? That is the first thing, we should have a tape. Okay, we should have a tape like this. By tape I mean a physical tape, which you had in that type recorders or something like that. You had these radios where you put these cassettes, they had a tape on that, magnetic tape, whatever it is. So if you had tape, what operations can you do? So you should be able to move left, you should be able to move right, you should be able to move this tape. This is one operation. Moving left is an operation, moving right is an operation. Okay, then you should be able to print something onto it. Okay, you should be able to print something on the tape. You should be able to write on the tape basically. Maybe in terms of magnetism or in terms of electrical currents. So howsoever you write, it doesn't matter, but you should be able to print something. And then you should be able to scan it. Scan basically means you should be able to read it. Okay, read the symbol on the tape. The printing means you should be able to write the tape. Okay, on the current position. Let's suppose you have this head is on the tape. If the people are from my era, they know this sort of thing. They had the tape recorder. Once we put the cassette on, and then you played the button. So there is something tape was moving. So what it was doing is, it was basically scanning that, and it was reading that. Printing basically means you write something on the tape. Scan means you read something on that. And there should be one more operation, that is erase. You should be able to erase. You should be able to somehow override the things. And the last thing is, you should have no operation. If you see, these are 6 operations. Okay, these are 6 operations. 1, 2, 3, 4, 5, 6. So what Alan Turing said, if you somehow give me a machine which can do these 6 things, I'll be able to compute everything that is computable. Okay, and there was a mathematical proof for this. Okay, so if you have a machine, if you have a tape like this, and you can move the tape left, you can move the tape right, you can print something on the tape, you can scan the tape, you can erase the things on the tape, and you can have no operation, basically do nothing on the tape. These are the operations. So if you give me these 6 operations, so that's what, anything that is computable can be computed. Isn't this amazing? How many of you felt this is amazing? Did you feel it is amazing that if you give me 6 operations, anything that is computable, you can compute it? Whatever is computer, you can perform addition, subtraction, you can perform machine learning, whatever you want. You can only do by this. Okay, everything, these are called as Turing machines. Okay, these machines which support these operations are called as Turing machines. They have a tape and a read write head. They have a tape, whole tape is there, and then they have a read write head, so where they can perform these machines. So every machine that you have right now, they are equivalent to Turing machines. A big statement is there. So every computer nowadays, every computer, or I'll say modern computer, is equivalent to Turing machines. So you now have an idea what Turing machine is. The Turing machine basically is having a tape and it has a read write head. Okay, and it can move this tape and it can perform these 6 operations. It can move the tape left, it can move the tape right, it can print something on the tape, it can scan the tape, basically read from the tape, and then it can erase from the tape, and it can perform no operation. And these are the 6 operations. Any modern computer that you have, even with the huge graphics cards, and if you have data centers, they're all equivalent to Turing machine. What is the meaning of equivalence here? By equivalence, I mean that whatever is computed, whatever is possible on your computer, it is possible on the Turing machine also. So this Turing machine was mechanical. Okay, it did not have electrical parts probably. Okay, some things were moving there. Okay, from these things we came to programming languages. Okay, now instead of these primitives, we came up with different set of primitives. We basically did the same thing. Okay, we had some memory and we could do these things. So real programming language, they offer more convenient. So there was convenience now. Okay, and because we shifted to the digital era, and now once the digital era was there, and now we came up with the more versatile set of primitives. We came with more set of primitives. So what was these most set of primitives? So let's suppose we had functionalities like, let's suppose, if else, loops, and we had data structures. But the whole point was they only were equivalent to these 6 operations. Whatever you do in programming, it's equivalent to these 6 operations, nothing more. Okay, so if you are let's suppose having control flow, you have these if else, you have these loops, or you have data structures, arrays, lists, whatever you have input output operations. All these things are primitives which modern language support, which C, C++, Java, Python, JavaScript, each of these languages support these operations. But all these operations are somewhat equivalent to this. That's why all these languages, once these machines are able to perform these operations, they are equivalent to Turing machine. Okay, now we combine these primitives. Once we combine these set of primitives, we allow programmers to combine these primitives to create new operations and new functionalities. Okay, basically we do nothing. We have these operations defined on us, and all of them are equivalent to this. Okay, how are they equivalent? It will again take me probably a semester long course is there, which where I can convince you that all these modern language, whatever there is, they are equivalent to a Turing machine. Okay, then we'll have to know about what is finite automata. Okay, and then we'll have to see what is called as deterministic finite automata. Then we have push down automata. From there we came up with Turing machines, and there's a lot of things that get involved. Okay, the whole thing is studied under called as automata theory. I'm just giving you a bird's eye view. Okay, what is coming, what led us towards this road, towards this programming. Okay, so once you have this automata theory, then you can build compilers. Once you have the thorough idea about what is computable, what is not computable, and stuff like that, then you can move on to compiler designers. Okay, the thing is now we have more set of primitives. What you give these programmers is you give them these set of primitives, and now programmers combine these primitives to create new operations. Okay, this can be achieved by using functions, procedures, classes, modules, libraries, whatsoever you see. They basically are just doing one thing. They are combining these primitives. Okay, so we can abstract these complex details, and then we can make these reusable components. Okay, then we have this universal programming language came into picture. Okay, so now because you know that we have something called as Turing completeness. Again, not wanted to discuss these terms, but it popped up in my head, so it's all right. So Turing completeness. So Turing completeness states that any computation that can be performed on one Turing system can be also performed on other Turing systems. That I said indirectly in that if you have a modern computer, if it can compute anything, it can be computable on a Turing machine. Okay, now you see that modern computers have these ALUs. They can add, they can subtract, multiply, they can read, write, buses, everything. But Turing machine is so simple. You see there is a tape, there is a head, it can perform these operations, and I'm saying that both of these things are equivalent. I'm not saying they're faster. Faster is something else. Today's modern computers are faster. Why? Because of the digital design, and because of the current flowing is at very rapid speed. So, and if you move these mechanical parts, there will be error rate is high, and all these things will be there. But still, what is computable on Turing machine is computable on the modern computers. Okay, that's what is called as Turing completeness. Is it all right? Everybody with me?
I have two questions. So the first question is, could you please?
Now we can start the language. So you saw we had a whole roller coaster journey where we started with these machines, and we had to put a lot of thinking. By we, I mean humans have to put a lot of thinking in order to get to the today's world where we have these computer languages. Okay, so if you see any language, now you have to speak with these machines. I said that there are Turing machines now. Today's computers are equivalent to Turing machines. So now what we have is we have to learn a language. Okay, so in the study of language, if it is natural language, let's suppose like English or Hindi or Urdu, Arabic, whatever it is, there are several aspects that dictate or delineate their structures or functionality. Okay, so the first thing is we have some primitive constructs. Okay, in the linguistics, the primitive constructs are maybe some letters, and then letters are combined to form words. Then these words are combined to form sentences. Sentences are combined to form paragraphs, stories, and stuff like that. But it all starts with these primitive constructs. Okay, so every language is like this, whether it's a natural language or if it's a programming language. Both of these have to have some primitives. They have to have primitive constructs. So what I mean by primitive construct, in the language you can easily see that we have, in the English language we have this A, B, probably C, D, something like this, and then we combine them to form words, and these words are accordingly combined, and we can get a whole story and we make sense out of it. Similarly, in this programming language we'll have primitives also. There we'll have primitive data types, we'll have some operations, primitive operations defined and stuff like that. Okay, and this is more sort of mathematically defined. So I said in mathematics what we have a language defined, and then we have operations defined. That's why in the programming language we have the similar stuff here. So we'll have some lingo which we call syntax, and then we'll have some operations on that. The first thing that will go is with syntax. Okay, so what is the syntax? So syntax says that there's a structure or arrangement. So what is valid? Okay, what is a valid expression within a language? What is valid within a language? So what is valid within a language? What is valid within a language? That's what syntax dictates. Okay, so you have to adhere to these rules. Okay, if there is some syntax that there are proper definitions. Let's suppose taking example of English. So English has dictated some grammatical rules, and you have to have these rules. Okay, so that's what syntax is. So here let's suppose if I just form some sentence, cat dog boy, cat dog boy. This is not syntactically correct. Why? Because it's just bunch of words put in some random order. So here you don't respect the grammatical, you don't accept basically you don't respect this grammar of the English. There is a particular grammar in the English where we see that there should be a structure associated with it. So this will be called the syntax error. Okay, so there are some valid rules written in the language, so you don't adhere to those rules. So here this doesn't make sense to us. But if we say, let's suppose cat hugs boy, so now it makes sense. Okay, now you put in it because it confirms with the grammatical orders. There is a grammatical order, you write subject, verb, noun, whatever it is. So you can see that here this makes sense and this does not make sense. So here we call this as a syntax mistake. So there's a syntax mistake because there are rules which we somehow broke. Okay, so the arrangement was broken down. So let's suppose we had noun, then we can add, let's say, verb, and then we can add noun, verb, noun, something like this. Noun plus verb plus noun. Let's suppose this is valid. By no means I am claiming that I'm an English expert. Probably people might find difficulties, but what I'm saying is that there are rules defined. So if I write noun, then I write verb, then I write noun. So probably it is syntactically correct. So if you see this, cat hugs boy. So cat, if you see, is a noun, hugs is a verb. Let's say boy again is a noun. So this is a syntactically valid statement. But if you see over here, this doesn't make sense. This structure is not respected. So here what we call, this is called as a syntax error. Similarly in the programming, when we see Python, if you just write this hi, and then you write, let's suppose 5. So this is the string which we call in program a string. So this is called an integer. So this again does not make sense. Okay, this does not, because there is a syntax error now. Syntax error. Why? Because it does not adhere to some rules of the some rules of programming language. Because programming language also have some rules, somewhat like grammar. Okay, it's not exactly like grammar, but there are some rules. So what are the rules? So now the rules are, you should have an operand, plus you should have some operator, and then plus operand. So this is one operand over here. There is no operator within, and then an operand, and then it does not follow that structure. So if I write something like hi multiplied by 5, so this is valid in Python, okay, because it adheres to these rules. And the first of error that you will encounter, okay, you will encounter syntax error. I'll write errors over here. So when you will be writing the program, the first type of errors, easy to catch. Even compiler and enterprise, they do catch it. So these are the syntax errors. So you probably might miss commas, you might miss semicolons, you might just spell the word wrongly. Okay, if there's a keyword, you can just name it differently. So there is a syntax error. So these are easy to catch, not difficult errors. So why are these errors coming? Because we don't adhere to the rules. So in terms of language, English language, there is a grammatical rule that we have to follow, and that you can see over here, cat dog boy, it is not a valid sentence, so there is a syntax error. But if you see this cat hugs boy, so here you see that noun plus verb plus noun is there, so it adheres to the grammatical structure of the English language. That's why this sentence is correct. Similarly, in the language, if we just have two operands and there is no operation between, okay, that there is no operator in between, so we said that this is not syntactically correct. There is a syntactical mistake. So here if you see this hi multiplied by 5, so this will perfectly execute on Python interpreter or Python compiler. The second thing is we have what is called as static semantics. So what is static semantics is now probably you will be adhering to the rules, whatever the rules of grammar are, you will be adhering to these rules, but still it won't give a meaningful thing. Okay, let's suppose I'll say I are hungry. In the English you will see I are hungry. So this doesn't make sense. Usually you will see I am hungry. But if you see that here we have just used some other form. Okay, that's what makes it wrong. This is what makes it wrong. If I wrote I am hungry, it would have made perfect sense. Similarly, in the programming language, what you can do is you can sometimes do a thing which can have this static semantic error. So what I can do is I said you can have operand, operator, and operand. So what I write, if I write hi plus 5, so this is not allowed in Python. Maybe it is adhering to the rules of grammar. What are the grammar I said? What are the syntax it had? Syntax is correct over here. This is operand, this is operation or operator, and this is again operand. I'll say OPR. Okay, operand, operator, and now you can see that syntactically this is correct, but you can see that this is not allowed in Python. Okay, that's why it's called a static semantic error. Okay, these errors are called as static semantic error. I hope that you understood by this analogy. So you saw that in English this I was perfect, but here you use some other form. If you use I am, so hungry, so this will happen correct. Okay, but grammatically if you see this is correct. So grammar it follows that whatever the structure of the sentence should be, the structure is there. But now you have used some other word in this place. So you saw that I are hungry. Basically if you use some other conjunction like I am is something like that, it will make sense. Okay, so now if you say I am hungry, this will make perfect sense. So there is no static semantic error. Okay, so it occurs like static semantic errors, they occur due to these illogical constructions. So we construct, but it has some like illogical construction within it. So in programming language, expression like this, so they may be syntactically correct, they may be valid syntactically, but static semantics is not correct. Okay, because there is incompatibility between data types. So this is a string data type and this is a integer data type. You cannot add them together. Okay, and then we have full semantics. That's called as full semantics. So what is the meaning of full semantics? So this basically is when it is syntactically correct also, when it is semantically correct also. So you have syntactic correction, that is it's right away semantically syntactically correct. It is also static semantically correct. So both of these things are, so syntactically it's correct, and then semantically, usually we call it as static semantically correct. So both of these things are there. But whatever you want to achieve with this, it is not giving the exact result. Sometimes you may think that I am writing something and programmer even writes that and machine executes it, but still what happens is the result given is wrong. So these are the dangerous errors. Okay, because compilers and these won't throw the errors, but whatever you expected. Okay, let's suppose you said something, you have to do something, but what you did is instead of minus you put some plus, you made a logical mistake there. Okay, what you did is you thought you were thinking something and you made a big mistake there. So that mistake would be called a static semantic full semantic error, basically full semantic error. These are very hard to catch, and usually when you will get to a level of programming, you will make these sort of errors more. syntax errors that are catched by a compiler. Even now you have these integer development environments where you will just write the code and they'll just underline this thing. And then we have the static, and sometimes they also are these things are also captured at runtime probably or something like that. But these full semantic errors, you'll have to bang your head on the wall. Sometimes there will be a slight mistake, but that expression will be semantically correct, that will be syntactically correct. Now you will see that it does something which I don't intend it to do. Okay, it does something which was not in your head, and these are very hard to capture. They are called as full semantic errors. Okay, now I said that there are 3 types of errors. The first type of error is called as syntax error. So syntax error are common mistakes that programmers usually they are characterized by some violation of rules. Let's suppose you miss some semicolon, or instead of if you wrote only I or something like that. So they're easy to catch. And I'll also write full semantic errors. So these are the errors that are easy to catch, because usually compiler will throw an error, or maybe if you are coding in some IDE integer development environment, there you will find some underline, okay, because it does not recognize that word. Then we have these static semantic errors. So static they occur when that expression or whatever you are evaluating is semantically correct, but it violates some rules. It violates some semantic rules. Okay, like semantic rules like this is one operation string, and this is one this is operand string, this is operand integer, but integer and the string cannot be added together. So it's a semantic mistake. Okay, syntactically it's correct, but there's a semantic mistake. Okay, so these static semantic errors, they can lead to sometimes unpredictable behavior. Okay, they'll throw some error at runtime. Okay, and maybe they can crash program. But sometimes they can also give incorrect outputs. But the most important are these full semantic errors. While the errors is not being caught, but whatever you are intending to do, it is not doing that, and that is the mistake of the programmer. And sometimes programmer writes something, and if he does a mistake or blunder in somewhere in the line, and he is getting some results, but what are the results he's getting? These were not intended results. Okay, you should be very careful about these errors. Okay, these 2 errors are kind of okayish, but the first point is that here this is very easy error, a little bit difficult, way difficult. If you are stuck in this, and you will have to probably cry for multiple days if it's a huge code base. Okay, and this is usually where I cried most. And I had a semantic error, and suddenly I woke up in the middle of the night. I felt, oh my god, there is that mistake in the code. I just opened my laptop, coded up, and it worked. Okay, so these errors are very difficult. So now you saw these types of errors will occur, and now people will see that there is compile time error, runtime error, all the errors will come into this. So either you have syntax error, you'll have static semantic error, okay, or you'll have full semantic errors. Okay, now we'll come to the programs. We'll write programs now. Okay, and after that probably we'll be moving on to the next session, and we'll close the recording. Okay, now what is the program again? So even if we are talking about Python program, if we're talking about C++ program, a program is again nothing but a sequence of definitions of the commands. This is sequence of definitions and commands. You will write something line by line. Okay, definition will have, like, let's suppose, what I mean by definitions, it will be having something called as classes. We'll see everything about this. Classes, probably functions. Usually we call them as functions also. So it will be having variables or something like that, and a lot of things will be there. So commands will have, so these commands will be given to interpreter or compiler. Okay, there will be something, let's suppose we'll say if do this, and then it's a command basically. Okay, commands, they're also known as statements or instructions, so we can call them as statements or maybe instructions. Okay, but what is a program? It's nothing but a bunch of a sequence of definitions and commands. Okay, how do these programs execute now? So I said that there is a whole level of translation going underneath. So when you have high level language, so high level language is being written, and after that it goes through a phase of translation. So the translation happens, it goes to machine code, and machine code is what basically computers understand. Okay, now in the Python, what you will see is we'll be mostly dealing with Python 3. Okay, Python 3x. I think now there are different versions. This is what we'll be reading about. Okay, and every language is a design philosophy. So with this, I'll conclude the session. So every language is a design philosophy. Whatever the spelling can be wrong, and I should not be blamed. Probably computer should be blamed for that. So what I'm saying is every language has a design philosophy. Now we are moving slowly to Python. Okay, so what Python, the design philosophy of Python was ease of programming. Ease of programming. Whenever you probably, like, let's suppose you are well equipped with this compiler design and stuff like that, and you would like to create your own language. Okay, and now you want to have own language. Then now we should have a design philosophy. Why are you creating a new language? Okay, if these many languages do exist there, why should you create a new language? So that was the question that Python inventors, they have to answer first. What is there in the language? What should this language do? So the first thing they said is we should make this easy, and the inventor was a mathematician. That's why you will see whole of the syntax of Python is like mathematics. Whatever set theory you studied, whatever functions you studied, more or less, this will somehow match or have a comparison with this. And I'll show you that if you write something, it's probably a mathematical expression, just translated in English. Okay, so he was a mathematician. He was inspired by maths, so that whatever we write in the maths, we sometimes write, let's suppose x such that x belongs to this, and for all these symbols you will there. You'll see in the Python. The design philosophy of Python is ease of programming. For Python, it doesn't matter if your program runs slow, if your howsoever your program runs, but if it makes the programming to run program to for a programmer it should be easy, then it won't care about that. The only goal of Python was this, that programmers should find ease. That's why, because of this, Python is slow. The whole design philosophy of C was to make like programs really faster. We should have really faster. So if there is a catastrophe and if it has to do something and it makes program faster, it will do it. And probably if I had time to show you that C does it, C will delete many other things to make the program faster. But if you see this, so there is the ease of programming. Because of this ease of programming, this is somewhat slow than other languages like C, C++. It's way slower than that. Okay, so this is the design philosophy, and probably in the next class we'll take up different things about Python, and we're not learning per se Python. What I'm teaching you is art of programming. But for that I'll use Python syntax only. I hope that everybody enjoyed this lecture. I'll just stop the recording over here. If there are questions related to this, I'm willing to take that.